Hi class, welcome to section 5.9, integration by parts, the very last section of this course. So, as I was saying, last section 5.8, we have been taking antiderivatives of pretty simple functions, right? So what do we do if they get if the functions that we want to find the antiderivatives of are getting a little bit more complex? So products of functions, compositions of functions, that's what 5.8 took care of. Integration by parts is simply the reverse process to the product rule, okay? So we're not going to have a reverse process to the quotient rule. That's also because really every quotient can be written as a product. So hopefully that works. Can do that. So the thing is, again, not every product inside an integral can be found. I mean, we can find the antiderivative of a product using the backwards of product rule, integration by parts, just because it's a product. So again, just as in section 5.8, the problems have to be just so. So let me take you through the process. What was the product rule? The product rule was that if you take the derivative of a product, what do? We take the derivative of the first times the second left alone, plus leave the first factor alone, times the derivative of the second factor. So that's exactly what we're going to play with. So what I've done here is I have written the same exact thing for you, but just using the Leibniz notation. And that's because, as you saw in the last, or in this chapter, we like that notation a little bit better. So the derivative with respect to some x, so these are all functions of x, so it's a product of some kind of functions. It could be anything. Let's say ln of x times x squared, right? So two functions of x. So the derivative with respect to x, you leave, it's, okay, they're actually written a little bit backwards here, uv. You leave the first one alone, take the derivative of the second one, plus leave the second one alone, take the derivative of the first. The order doesn't matter, but you take the derivative of one of them at one time. So, right, that's just u times v prime, and that's v times u prime. That's what that stands for. Good. So let's just kind of pretend that we are multiplying the whole equation by a dx. It's a derivative. We're just simplifying, just making it a little bit easier looking. But the same thing what we're saying here is that the derivative of a product is take the derivative one at a time. Yes, so we keep one factor alone, the other one we take the derivative of. So what I want to do is integrate the equation. So in other words, throw an integral on both sides. And sure, like we did with the chain rule, by the way. So basically what I'm saying is, right, that these are equal to that, then the integral of this side is equal to the integral on this side, yes? And again, when you take the antiderivative of a sum, you get to distribute that integral to each side. So sure enough, what happens with an integral and a derivative? They cancel each other out. They are inverse processes of each other. So a derivative and an antiderivative undo each other. Yes, so just as we said, you take the integral of a derivative, you just basically back to your initial function, right? So we throw derivatives in an integral just to get the initial function back. So they cancel each other out. So this is the derivative. Yes, I can't cancel these because it's not the derivative of the whole thing. It's just one part of it. So what we get is simply our product uv backwards. So what we're going to do is now solve for integral of u dv, and that's also really maybe why we left it that way. So you leave the first one alone, take the derivative of the second one. So to solve for this term here simply means to do what? Minus this guy over. So the integral of u dv is u times v. So the integral of u dv is u times v. So again, all I've done is just solve for this term right here, right? Keep this guy alone. This guy has to be moving over. So it's really not that complicated, but right here is what we call the integration by parts formula. All right. So that simply means that what? Remember, what are we starting with? We are starting with integral. We want to find the antiderivative of some function. So we will start with some integral. And what we're saying is that according to this formula, we're not starting with a product, right? And turning it into a derivative. We're starting with an integral. So what we are saying is that we will start, I'll write this down. We will start with an integral. So we will start with an integral, there it is, in which we have a product. I see a product in here, u times dv, between a what? Between some function, let's call it u, and the derivative of a different function. We'll call that dv. And that's when integration by parts works. That's when we recognize this. So again, one more time, I did write it with the integrals and so, but just to simplify basically your computations here, what do we start with kind of thing? And you could have started right here as well. I'll just write it on the side. I don't know why I feel like maybe that's confusing. So I'm starting with the derivative. I'm starting with the derivative of the product rule, right? So what we're doing is we are solving for one of these terms. So what does u times v prime equal to? U times v prime is simply going to equal to uv prime minus u prime v. So all I'm doing is just solving for this term, yes? So I'm throwing this guy over. And now I'm taking the integral on all sides. So what's going to happen? I have the integral of a function and the derivative of another. Here I have an integral of a derivative of the whole thing. These cancel each other out, right? So an integral and a derivative cancel each other out. So I'm left with just uv minus simply the integral of the derivative of u this time times v. So they swap. And this is your integration by parts formula. So as you notice from this formula right here, which is exactly the same thing I wrote, except for instead of v prime, I wrote dv. So what's going to happen in this formula right here is that we're going to be starting with an integral, yes? And then in that integral, we will see a product. And what we're going to do is we're going to turn that, it's going to say it's equaling to, fine, some product of two functions, that's going to be some term that we now have, minus a different integral. So we are getting a second integral to evaluate. We're not done, right? We still have an integral. So we're getting a second integral, which hopefully we already know how to solve. Which we hopefully can solve. Okay, so I'd say we just do a problem and see what all this notation and all this theory is all about. So here it is. Wanting to use integration by parts to find the indefinite integrals. In other words, the antiderivative. So if you look at this, what do you see? I see the product between two functions, x and e of x, which are different types of functions, so they cannot be multiplied together. So what I need to do is I need to find the antiderivative of this product. Well, we don't have a backwards product rule, right? We don't have a product rule for antiderivatives. Yes, we know how to take derivatives, but we don't have a rule for antiderivatives, except for We just figured one out, and that's called integration by parts. Now, I also want to point this out before we get started. We certainly dealt with a bunch of derivative products inside integrals in the last section, okay? Why didn't we use integration by parts? I'm going to see if I can find the notes from 5.8 really quick. Here it is. This was our 5.8. And here's a product right here. What's the difference between 5.8 and 5.9? In order to solve the problems in 5.8, what you need to recognize is this is going to be a composition of two functions backwards. So it's the chain rule backwards. So what do I have to see? Yes, I have to see a product. One of the factors should be a composition of two functions. Yes, a polynomial inside a power. And what else do I have to see? As a second factor, I have to see the derivative of the inside function. That's when I recognize the chain rule backwards, right? The U substitution is what we call it, right? When it comes to integrals. This is a product, but it's not a product between the composition of a function and some other kind of function. E to the x is just the same, e to the x. X is x. These are not compositions of functions. And also, this x is not the derivative of the inside, right, of that little x. The derivative of x would be 1. So that's a perfect example for when integration by parts works. So what did our formula say we have to do? We have to look at this. It said we will start with an integral in which we have a product, right, between what? A function, u, and the derivative of a different function, dv. So our goal, as a matter of fact, will be to recognize who is u and who is dv. So let me call this a blue part. Okay. And we're going to have to be also pretty smart about who we choose to be u and who we choose to be dv. So as a rule, and it's in your notes, I put up different scenarios. It's a little table. If so, then that's your u, that's your dv. So please look at that. But the point is you want to, between x and e to the x, who should be our u and who should be our dv. So the rule of thumb is always you want to choose u to be the part of this product that's going to disappear once you take its derivative. So if u is x, what is the derivative of u with respect to x? 1. In other words, remember how even in the substitution method, we started writing the dx over. So yes, du is equal to 1 times dx. And we're going to take that shortcut and write this as well from now on. Good. So we chose x to be our u. What else did we say we have in this formula? The rest of it should be a dv. So then who is dv? Well, the rest of it, e to the x dx. So really, if you take it backwards, what you really have here is a dv over dx is e to the x. So this is nothing but the what? The derivative of the function of some function v. Now, if I am given the derivative, how do I find the function itself? So that's the derivative of some function v. What is the function itself? Well, the function itself is the antiderivative of it. So the antiderivative of e to the x, by the way, is itself. Now, sure enough, you would have to add a constant k at the end, but what we're going to do is not add the k in between. We're just going to add it at the very end of the problem and not have to deal with it in between. Okay, so this part is your x, is your u. This part here is your dv. So I'm going to write the formula for you one more time, okay, just so we can follow it. So what was the formula that we had, the integration by parts formula that we had on the previous page? It said we had the what? Integral of u dv, which is what we have, is going to equal to what? is going to equal to your functions uv minus, swap them, v du. Okay, all right. So let's substitute all of this. So this is my integral of u dv, and that's supposed to now equal to u times v. Do we have u? Yes, u is equal to x. Do we have v? Yes, right here we found it. V is e to the x. Minus, the second part of it is another integral. What do I put in the integral? V, where is v? Right here. V is equal to e to the x. Du, did I find du? Yes, right here. I found the derivative of u. The derivative of u is dx. And look how pretty this is. It's all in terms of x's. It's got the perfect notation. Yes, integral and a dx. It's all there. What else do I have to do? Well, I have to continue. So I have x e to the x. That part's done. Yes. What do I need to do? I need to find this second integral. But this second integral is much easier to find than the first one. Why? Because we got rid of x. Yes, so it's not even a product. It's something that we know what it is. The antiderivative of e to the x is e to the x. And there it is. That's your answer. So the idea one more time, and of course we'll go over it again. The idea one more time is that what? You have a product of two pretty simple functions, but to take this antiderivative backwards, or integration by parts, what do? We're using this formula right here, okay? Which says it's what? It's uv, right? So your two functions. So out of u, you create du, and out of dv, right, the derivative, you create your v back. Okay, so you have all the parts, u, v, du, dv. You have all the parts in this formula. You have u, v, du, dv, right? That's all you need. Okay, and when you plug it back in, you have a second integral to evaluate. That second integral should be something that's easy to find, which it is. If this second one turns out to be even more complicated than your initial problem, then you made the bad choice. So you had the factors backwards. So maybe you wanted to call by u the second factor and by dv the first factor. Okay. So what I want to do before we move on is check if this is indeed the right answer. What do I mean by check? Take this function here and take its derivative. See what we get. So what's the derivative of this? Well, I go term by term. Well, the first term is a product, so I have to use the product rule on it. So the product rule for this product says take the derivative of the x, which is 1, times e to the x, plus, leave the x alone, times the derivative of e to the x is e to the x. Plus, move on to, oh, sorry, it's a minus. Minus, move on to the next term. What's the derivative of e to the x? The derivative of e to the x is itself, plus some constant whose derivative is 0. Okay, so let's see, what do we get here? Well, there's a 1 e to the x minus 1 e to the x. They cancel out. So I'm left with x e to the x. So was that the initial problem we had to solve? Yes. A little bit scribbled over, but you have it in front of you. Yes. Okay, so let's try this again. So the secret will lie into who do you make a u and who do you make dv. So in other words, between these two factors, which I'm going to rewrite for you because of that square root, so I have an x to the 1/2 and I have an ln of x. Okay, so between these two factors, one should be my u and one should be my dv. And out of u, I'm going to create du, its derivative, and out of v, I'm going to create v, its antiderivative. Okay, so what do you think? I want u to be a function. I want you to choose between these two. U should be the one factor that's going to pretty much disappear. So what is the one thing you don't want to see again in the second integral? Definitely the natural log. And by the way, that's one of the rules. If you have an ln in any of your problems to solve by integration by parts, you always choose ln x to be your u. It's in those rules I put in the book as well. So let's see, why is that? Gonna work just fine. So if u is ln x, what's du? What's the derivative of it? Is 1 over x. Remember the x? So I could write du over dx and then multiply the dx over, but we practiced on this already in 5.8, so I feel safe that we could do that. Now, so this was u, right? That means the rest of it, which is what? X to the 1/2 dx, yes, is the derivative of v, right? So see how the dx part has to go with it because it's a dv over dx is x to the 1/2. So what do I create out of the dv? I create v by, so the derivative is this. Then the function itself is its antiderivative. So what's the antiderivative of x to the 1/2? Is x to the 3/2 divided by 3/2. Okay, which again, I can fix it a little bit, but I'm going to leave it like there. I'm going to fix it here. So this part here was your dv. Okay, so I'm going to write the formula just because it's much easier to me if I know what to follow. So this was my formula that said what? The integral of some u dv, which we chose already, is u times v minus, swap them, v du. Okay, so there you have it. Okay, so I have that integral of some u times a dv, and that's going to equal to what? U times v. So I'm taking all these from here. What's u? U is ln x times what's v? V is this guy right here, which I'm going to fix right here for you, 2/3 x to the 3/2. So again, that's your u, that's your v, yes? Minus, it says, continue on and write a second integral. What's the second integral? V, which is this one here, 2/3 x to the 3/2 times du. What's du? Oh, du is right here, is 1 over x dx. Perfect. I don't see a natural log. Even though it's a product between x's. So the same type of function we know, right? Power functions, we know how to put that together. So I'm going to continue here. Just to make it prettier and less confusing, I'm going to write the 2/3 x to the 3/2 at the front. And now it's clear that it's not multiplied to the x values inside the log, but to the log function itself. So it's outside of the log, basically. Minus, I'm going to rewrite this. If I put these together, what do I get? I get a 2/3. What does that mean? X to the 3/2 times 1 over x. When you basically divide, right, this is an x to the top, that's an x to the bottom. To put these x's together, we do so by subtracting the exponent. So 3/2 minus the 1 from down here is an x to the 1/2. Okay, all right, dx. Okay, so put those x's together simply by using rules of exponents. And there we have it. So is this second integral that we still have to finish off something that we know how to do? Yes, it's not a product anymore, right? It's just one term. So the answer is 2/3 x to the 3/2 times ln x minus 2/3 times x to the 3/2 again times 3/2. And now you're welcome to throw the plus k. Again, we could have kept it here and put it here and put it. We don't want to do that, right? We just want to keep things simple. Throw the constant at the very end. So I'm going to still do a little bit of algebra. Again, dividing by 3/2 means to multiply by another 2/3, so that makes it 4/9. There you have it. Okay, so there you go. Okay, all right, let's continue. So maybe we should start a different video for these last 2 pages.